He did well.
To all, first and foremost, I would like to thank Dr. Shailesh for giving me this opportunity to talk to all of you that how space can be used in terms of understanding the active dynamic processes which are going on the surface of Earth, which are manifestations of deeply, darkening processes. Either it can be related to the earthquakes, or it can be also related to landslides, or it can be also related to anthropogenic activity. So I will be just briefly talking about that how space technologies over a long period of time has evolved, and now it's providing you the information about these very subtle deformations which are happening at the scale of millimeters to centimeter scales can be captured. This is simple, tectonic and lithospheric setting of India, and as you have heard in the morning, we have this mighty Himalayas where large amount of thrust and strain accumulation is happening. But at the same time, you have various other, features within the oceans, the Indo-Sumatra Arc zone over here, and then of course this whole region, which is basically tectonically very active, and then Sumit talked about the intraplate tectonic activities all across India. Just to tell you that it's not the earthquakes which basically troubles us, it's basically the buildings, or the density of the population which troubles you. As you can see, this area is very densely populated area, and the kind of strain which basically gets accumulated because of the tectonic movement needs to be monitored on a very large scale, at a very fine scale. We talked about micro-resolution. So this is the kind of strain built up which is happening all across Himalayas because of various amount of earth processes which are happening, and of course people are talking about the seismic gaps. Where are the seismic gaps? Large amount of earthquakes have happened in this region which have released this strain. But how we can measure this strain, it's a big question, because morning Dr. Nayak was talking about. So we need to integrate various technologies. Space observations have been providing information about Earth's surface in various parts of electromagnetic spectrum. We have this optical image window, we have the microwave window, and combining these data sets, along with the GNSS, or the what we call as GPS, commonly used term for American constellation. We have our own, Navic constellation, which also provides you the information about the, the movement if you put a receiver over the ground, which basically measures the signals which are sent from the space. So if we can combine all this information from space, as well as, the GNSS-based observations and the seismological information. See, there are two ways of addressing this issue. One is the acoustic waves which propagate. You can measure through seismometers, and you can make measurements of these deformations either through a GPS-based network or GNSS-based network, or make these small deformations you can quantify using the space-based observations, and try to solve this jigsaw puzzle of earthquake, landslides, etc. So this is a cartoon which basically explains all these processes. I will not go into details. Some of the youngsters can look into these things. But how Earth observation data or the satellite data has been helping in earthquake studies. So you have this, the optical imaging satellites which takes the picture of Earth in what you call the visible and infrared part of electromagnetic spectrum. We have very high resolution imaging capability today. I will show you some examples. We have synthetic aperture radars. The ability of radars is that they can see through clouds. They can work in day and night situations, which is basically not possible in optical satellites. And you have these navigation signals, which also can be used for what we call as the space geodesy. So in all cycles of this earthquake activities, this is very interesting picture. Today we are able to give contributions from space technology, either in terms of making continental strain rate measurements, or in terms of post earthquake what kind of damages has been happening. We are also able to measure the landslide processes. We are also able to quantify the surface creeping using these interferometric processes. And then after an earthquake has occurred, large amount of damage assessment and things like that are also being done. So there is a large amount of scope of Earth observation data in terms of understanding the tectonic processes, and once the processes happen, how these strains have been released. So I will give you a couple of examples of different technologies. If you are using optical satellite imageries, how you can make measurements of these deformations. So we have capability of detecting what we call as the digital elevation model, the topography from space using a method called stereoscopy. And before the event and after the event, if you make measurements and take differences, you can basically make measurements of these subtle deformations. And some examples I will show you. Many of you may be remembering this rock slide event which happened in Chamoli in 2021 in the month of February. The entire rock slide zone, we imaged before the event and after the event and created digital elevation models, and the digital elevation difference basically told us that how much amount of mass has slipped, what kind of deformations have happened, and we could quantify and tell that this much amount of material has fallen and which has triggered this particular event. So this is one such example of using space technology for calculating the deformations. This is another example of our Joshimat. I hope that NDM is not listening to it. We have been told not to speak in public, but it's not a public meeting as such. But using two different dates of very high resolution 50 centimeter data from a satellite called Pleiades, people are able to, scientists have calculated the rate of deformation in the Joshimat area. This is of the order of around 2 meters or so at the toe of this particular landslide zone. And this is the river over here. So you can see there is a very clear-cut demarcation between these two different images, that how the motion or the surface is moving using this type of measurement. I will show you the synthetic aperture radar measurements also over this area. And we can make these measurements over a period of time because we can get these imageries. Satellites provide you the opportunity of repeated observation. So you can basically create time series observations, and using these time series observations, you can basically understand the kinematics of these landslide zones. Another important thing is that after the event has happened, you can also make measurements of the rupture, how the rupture has propagated. This is an example of very high resolution data, 30 centimeter data over Turkey. You can see around this airport region how the zone has ruptured, and all this rupture length and the surface manifestation of these fault ruptures can be calculated using satellite observation. It's an animation. You can yourself see that how the surface has moved all along this fault zone using two different satellite observations. Another interesting technology is called synthetic aperture radar technology. Basically makes use of the larger wavelength of energy which can penetrate through clouds, and not only the backscattered energy, but the phase differences also can be used to quantify the surface deformations. And this is just a simple physics that if a point was here, this phase will be very different if the point has moved, And this subtle phase differences, which is basically produced by scattering of these waves, can be quantified in terms of making measurements of the surface deformations. So these technologies are called the interferometric SAR technologies, or there is another method called the differential SAR interferometry, where you remove the elevation information. There is another component called the permanent scatter interferometric technique. There is another small baseline interferometric technique. There are various techniques which are available for various purposes. So using these type of methods, where you can make measurements of one region from two different orbits of satellites, you can basically create this type of fringes, or basically the change detection maps. Essentially, whatever you are talking, you can visualize these changes by using these type of things, and the processes which are associated with the normal tectonics all along the tectonic boundaries or intraplanetary regions, landslide driven activities, as well as anthropogenic effects which were being talked about. All these deformations can be studied using these type of techniques. I will show you some examples. This is the work which we did around Chandigarh area. There is large amount of water extraction happening in the Indian cities, and you can see that in Chandigarh region, many of the residents are complaining that suddenly their houses are having these cracks. And so this is basically subsidence in various parts of Chandigarh, which is happening of the order of few millimeters to centimeters, which we can quantify and precisely make maps at a spatial resolution of around 30 meter by 30 meter grid. Mishraji was talking of micro-zonation, pico-zonation. So that's how the space technology plays an important role. And you can explain to the residents that what is happening, what kind of processes are leading to this. And we can also need to regulate the groundwater extraction. Some legislation and policy has to come. Otherwise, this type of issues are there. In Delhi also, similar work has been done. There are large pockets in Delhi which are basically facing large amount of subsidence. This is because of water. What about the landslide? So this is one work which is recently published by one of my students from IIT Roorkee, where this landslide which has happened in Sirmaur, we have basically done the the recreation or simulation after the landslide has happened. So we analyzed all the data as a time series data from a satellite called Sentinel and generated this permanent scatter landslide deformation analysis, in different phases of the landslides, and calculated the velocity of the movement. So these are the velocity vectors. You can see this is the zone, which is most dynamic zone as per this ISRO data sets. And this is the time series data. Using this time series data over this region, you can see that there was slow creep was developing, and suddenly there was an event which triggered this landslide, and all the deformation basically started happening in a large or accelerated manner, and this is when the landslide occurred. So using this type of time series data and by projecting this time series into space, you can basically pinpoint with an uncertainty of 4 to 5 days that when a landslide is likely to occur. This is of course post facto, when an event has happened. But maybe we can do many such experiments and understand and learn from these examples. Can be forecast, when a large landslide is likely to occur, where already the landslide vulnerability zoning has been done using space data by CBRI and NRSC and other people. So this is how the technology is progressing. This is an example of Joshimath. Using this again permanent scatter interferometry technique, that means you make scattering over buildings, which doesn't change over a period of time, but you see how these buildings have moved. This is how the situation looks like over the last 2 years. 2 years of data has been analyzed. This is the JP colony area where the maximum amount of deformation on ground has been measured. This is the Ravigram area in Joshimath. Those who are aware about the Joshimath geography, they can appreciate that. These are the two places where maximum deformation on the ground has been reported, and this is the data from one of the CORS station operated by Survey of India. It shows that there is a vertical movement of around 70 centimeters or so at many places. So these results are also corroborated by the ground observations. Similarly, for earthquakes also, imaging using these technologies has been done. These are examples of various earthquakes. This is the Afghanistan earthquake. You can see the upliftment and the downlift along the fault. The fault also can be imaged using the radar interferometry. This is the image of the earthquake of Turkey which has happened. Of course, these are the faults. Where you can see both the sides of the fault, the deformations are very different, and you can image the entire region and create what we call as the seismic hazard. Very fine seismic hazards of these areas. This is what I thought I will recommend that in India we should do it. See, this is the high resolution seismic strain map which can be calculated using the strain data. This is from the GNSS. When you combine GNSS with INSAR, you get much more precision. And you can see this is the North Antalya fault. This is the most seismic hazardous region in Turkey. And the recent the southern region over here, but there also the seismic hazard is equally dangerous, and that is what is the recommendation I would like to give through this workshop. This is a recent work done by Mukhopadhyay and all. Using 1,252 GPS stations, we have calculated a strain map across Himalayan belts. And you can see the hot spots where the strain accumulation is very high. But this is coming because even 1,200 is not a very dense network. So if we combine this data along with the radar interferometric observation across Himalaya, which is currently nobody is doing, maybe as a space agency we should take it up, but there is a lack of data. So Sentinel, there is only one satellite today, and that is where basically we will come out with zones where the strain accumulation is happening, and we have the past seismic data where we know that strain has not been released. And those reasons we can say that probably they can be the potential seismic hazards in future. So we are going to have a very wonderful mission, the most costliest space mission ever going to be flown. Next year there will be a launch of this NASA ISRO synthetic aperture radar mission. There are two frequencies, L band and S band. Those who are not into this domain, maybe you can talk to me later. These two frequencies, S band SAR is being developed by India, L band SAR is developed by NASA. These two frequencies basically will be combined and they will be used for studying various dynamic processes on Earth, including the solid earthing. And you look forward for this type of data sets. The launch date is already scheduled on 29th of January 2024. We are going to change. This will be a game changer for Earth science community. as far as the space observations are concerned. And these are the focus research areas which can be basically handled with the NISR mission. Every 12 days you will have a systematic observation, and 12-day time series of deformations all across Himalayas can be generated. This is the observation plan which has been fixed up for entire Indian region. As you can see, the most part of the tectonics as well as the Gujarat region, intraplate tectonic regions are going to be systematically observed every 12 days. We will be able to generate a product which we call as the deformation product, and all geoscientist community can make use of this product so that you can quantify the strain rates all across the Himalayan arc system. Thank you very much.
Very interesting.
Thank you, Prakash. I think you made a very important recommendation about combining the strain map along with the GNS. I think this we should take it up as early as possible. May I now request